Hi everyone, this is Som Prakash. Today I am discussing about the topic of a full wave bridge rectifier circuit without and with filter. Just coming to the topic, to construct a full wave bridge rectifier circuit and analyze its output. To analyze the rectifier output using a capacitor in shunt as a filter. Overview is, as you have seen already, a half wave rectifier circuit is unsuitable to the applications which need a steady and smooth DC supply voltage. One method to improve on this is to use every half cycle of the input voltage instead of every other half cycle. The circuit which allows us to this is called a full wave rectifier. Here unidirectional current flows in the output for both the cycles of input signals and rectifies. The rectification can be done either by a center tap full wave rectifier or a full wave bridge rectifier. In this experiment, we will study a full wave bridge rectifier. The full wave bridge rectifier is another type of circuit that produces the same output as a full wave rectifier. Is that of the bridge rectifier? This type of single phase rectifier uses four individual rectifying diodes connected in a bridged configuration to produce the desired output, but does not require a special center tapped transformer, thereby reducing its size and cost. The single other side, as shown in the figure, the four diodes labeled D1 to D4 are arranged in series pairs with only two diodes conducting current during each half cycle. During the positive half cycle of the supply, diodes D1 and D2 conducts in series, while diodes D3 and D4 are reverse biased and the current flows through the load as shown in figure. During the negative half cycle of the supply, diodes D3 and D4 conduct in series, but diodes D1 and D2 switch off as they are now reverse biased. The current flowing through the load is the same direction as before. As the current flowing through the load is unidirectional, so the voltage developed as the load is also unidirectional during both the half cycles. Thus, the average DC output voltage across the load resistor is double that of a half wave rectifier circuit, assuming no losses. And ripple factor, as mentioned in the previous slab, the ripple factor is measured of a purity of the DC output of a rectifier and is defined as R is equals to V by V DC is equals to V square minus V square by V square DC is equals to square root of V square by V square DC minus 1 is equals to the value. In case of a full wave rectifier, V RMS is equals to V maximum square root of 2 is equals to 0.707 value maximum. The ripple frequency is now twice the supply frequency. And next, rectification efficiency. Rectification efficiency, uh, mu naught is given by mu is equals to DC power delivered to load, where RD is the forward resistance of diode under the assumption of no diode loss. The rectification of efficiency in case of a full wave rectifier is approximately 81.1%, which is twice the value for a half wave rectifier. Next topic is a filter. The full wave rectifier circuit with capacitor filter is shown. The smoothing capacitor converts the full wave ripple output of the rectifier into a smooth D output voltage. The detailed description of its filtering action is already explained in half wave rectifier handout. Two input parameters to consider when choosing a suitable capacitor are its working voltage, which must be higher than the no load output value of the rectifier, and its capacitance value, which determines the amount of ripple that will appear superimposed on the top of the DC voltage. Apart from rectification efficiency, the main advantages of full wave bridge rectifier is that it has a smaller AC ripple value for a given load and a smaller smoothing capacitor than an equivalent half wave rectifier. The amount of ripple voltage that is superimposed on top of the DC supply voltage by the diodes can be virtually eliminated by adding other improved filters such as a PI filter. The equipment for the circuit components is a step down transformer, 4 junction diodes, 3 load resistors, capacitor, oscilloscope, multimeters, connecting wires, and last is breadboard. And next, let's coming to the procedure configuration. The full wave rectifier circuit as shown in the circuit diagram. Note down all the values of the components being used for the processor. Connect the primary side of the transformer to the AC circuit, mains and the secondary to the input of the circuit. Next, measure the input AC voltage and current and the output AC and DC voltages using multimeter for at least three values of load resistors. To choose proper settings of the multimeter for AC and DC measurements, feed the input and output to the oscilloscope. We will use oscilloscope here only to trans the output waveform and save the data for each measurement the input and output voltages separately, and here multiply the uh, AC at the input by square root of 2 to get the peak value and calculate DC using the formula VDC is equals to 2V maximum by pi. Compare this value with the measured VDC at the output. Next, calculate the ripple factor and the efficiency. Connect the capacitor across the output for each load resistor. Measure the output AC and DC voltages once again and calculate the ripple factor. Next, trace the input and output waveforms in oscilloscope and notice the change. If time permits, you could also use different values of capacitors and study the output. And thank you.